All right, back where we left off. You should have done these problems and not been a lazy sloth about it. All right, distribute. 4 times negative 2 is negative 8. 4 times 3i is 12i. Boom, negative 8 plus 12i. Again, distribute. 2 times 4, 2 times 3i. Negative I times 4, negative I times 3i. Okay, we're going to have to do some simplification before we get to our final answer, because we can't leave a 3i squared right there, because I squared is negative 1. Therefore, this term becomes plus 3. Final answer, 11 plus 2i. And lastly, another distributive problem. Hopefully you recognize that the middle terms end up canceling out, because this is the same thing here and here, except different signs there. So those two terms are going to cancel. This becomes plus 4. Our final answer is just 13. Alright, so hopefully you guys get the hang of that. Let's talk about complex conjugates. Alright, the reason we have to talk about complex conjugates is because we need it for division. You'll see why in a second. A complex conjugate is a complex number such that when it is multiplied by its partner, the product is a real number. The imaginary portion ends up canceling out. Okay? Guess what? Remember what just happened on that last problem? The imaginary part canceled out, and I was left with a real solution. That is what complex conjugates are. 3 plus 2i and 3 minus 2i, they are complex conjugates. See? All right. The original numbers that we have are complex numbers, but the product is real. All right. So first, let's just get practice at figuring out how to determine what a complex conjugate is. In order to do it, all you need to do is change the sign on the imaginary part. But don't believe me. Let this lovely table tell you. I'm going to give you a number, complex. You're going to determine what the conjugate of those numbers are, and then you'll see what the products of them are. All right, so again, all you're going to do to figure out a complex conjugate is change the sign on the imaginary part. So our first conjugate is 3 plus I. When you multiply those out, okay, remember the middle term cancels, so you end up with a 9 minus I squared. I squared is negative 1, so you end up with 9 minus minus 1, which is 9 plus 1, which is 10. 4 plus 2i, the conjugate, 4 minus 2i. The product, and hopefully you guys can get to a point where you don't have to distribute the whole thing, but 4 times 4 is 16. 2i times negative 2i is minus 2i squared. Oops, 4i squared. So that becomes 16 plus 4, which is 20. The complex conjugate of 5i, negative 5i. The product is 25. Complex conjugate of negative 5 plus 6i is negative 5 minus 6i, with a product of 51. All right, if you don't understand where the 51 came from, make sure you ask in class. All right, so what's the point of a complex conjugate anyways? Well, it has to do with simple stratical form. Remember that in simple stratical form, no radicals are allowed in the denominator. So that number right there is not allowed. All right? Because I is technically a radical if you think about it. It's a square root of -1. So in order to put this term in proper form, we have to get all imaginary components of it out. And the only way you can do that is to multiply by the complex conjugate. Now since it has a numerator and a denominator, you're going to multiply both by the complex conjugate of the denominator. So the number 4 plus 2i, we're going to take that and multiply it by the conjugate 2 plus I in the numerator and the denominator. When you do that, your numerator becomes 8 plus 4i. The denominator becomes 4 minus I squared, which is just 5. And don't forget to separate the real and the imaginary. 8/5 plus 4i over 5. That is how we divide complex numbers. All right, let's do a couple more examples. I just love this graphic with the curtains drawn back. Okay, anyways, let's try this. 2 plus 3i over 4 minus 2i. All right, we need to multiply it by the complex conjugate, which is to say the complex conjugate of the denominator. The numerator doesn't bother us. Remember, the point is you can't have a radical in the denominator. So we're going to multiply by 4 plus 2i. And there's a whole lot of distribution to be done here. In the numerator, we have some things that can be simplified, and in the denominator, we also have some things that can be simplified. Okay, 6i squared is -6. 8 minus 6 is 2. So the numerator, you get 2 plus 16i. The denominator, you end up with 16 plus 4, which is 20. And yes, if you can reduce, you reduce. So our final answer for that, when you divide, or when you reduce the numerator and the denominator, is 1/10 plus 4i over 5. Okay, let's try this one. Our complex conjugate in this case will be 2 minus I. Our product, we got 6 minus 3i plus 8i minus 4i squared. Middle term disappears and the conjugates on the bottom. We have 2 squared minus I squared, which is 4 minus I squared. This becomes plus 4. This becomes plus 1. Reduce if you can. 2 plus I. All right, let's try some examples where you're not given the term in a proper form in the first place. -3 times -12. All right. If you were to take and just multiply them both because they're radicals, you would have a negative times a negative, which is positive. You would get the square root of positive 36, which is 6. But that is not correct. You have to pull the i's out first. Should I go back to that graphic? It looks something like this. There was his eye socket. There was his eyeball. Socket, eyeball. Remember that one? Pull the i's out. Okay, so we can't just multiply straight across. Pull out the i's. We got I squared of 3 and I squared of 12. And you multiply those to get I squared, square root of 36. Okay, the square root of 36 is 6, but I squared is -1. So the final answer is -6. All right, next one. The square root of -48 minus the square root of -27. Okay, remember, addition and subtraction means they have to be like terms. They do not look like they are like terms right now, but let's simplify them first. Okay, we can pull an I out of each of them. 48 to 16 times 3. And 27 is 9 times 3. Square root of 16 is 4. The square root of 9 is 3. So yeah, this does actually simplify. 4i squared of 3 minus 3i squared of 3. Okay, again, we pull the 16, the square root of 16. Whoops. We pulled the square root of 16 out of this one to get 4i. We pulled the square root of 9 out of this one to get 3i. What was left inside was a square root of 3 in both cases. And if I have 4 of them minus 3 of them, I'm left with simply 1 of them. However, if the I squared of 3 did not match, you would not be able to combine those terms. Since they do, final answer, I squared of 3. All right, let's do another example. Say we have -2 plus the square root of -5 squared. Pull the i's out first. You guys take it from there and finish it off. Pause the video while you do it. Okay, what do you get? After all is said and done, you should have -1 minus 4i squared of 5. All right, let's do some even more complicated examples. You're going to love this. Ooh. Fractions with radicals. We got a lot of work to do on this one. So, it's best to simplify each fraction separately before trying to add them. Okay, you know how if you have fractions, you try to get a common denominator. That's not my recommendation. My recommendation is to work with them separately, simplify them, and then get the common denominator later. All right, in other words, I'm going to take that left-hand portion and multiply it by its complex conjugate. I'm going to take the right side and do the same thing. Okay, so I'm kind of just working with them independent of one another. I am not adding them yet. Okay, well, this looks like a lot. What do we get? We're going to get 8 minus 2i minus 12i minus I squared. We're going to get -18 plus 12i. The denominator here is going to be 16 plus 1. The denominator here is going to be 9 plus 4. So what is it going to look like here? Okay. Now you have them in proper radical form, and now you can get a common denominator and add them. These particular denominators, not the most pleasant looking things, but so what? We're going to multiply the left by 13 over 13, the right by 17 over 17, and simplify, because remember, we still have to do this addition, right? And so our final answer looks like that. And notice, once again, I separated the real from the imaginary. Lots of examples on here. Hopefully it helps. Let's do one more using the quadratic formula. Solve the quadratic equation 8x squared plus 14x plus 9 using the aforementioned quadratic formula. Why don't you pause the video and give this one a try on your own. Alright, well, as you know, there's A, there's B, and there's C. So when you plug the numbers in, it looks like that. We're going to get a negative under the radical, which means that we're going to have imaginary solutions. Okay, 92 can be broken down. What goes into 92? 4 does. Okay, we can reduce everything because everything's divisible by 2 to get this. Now, one thing I want you to recognize here, we got an answer that is negative 7/8 plus or minus I squared of 23 over 8, okay? Doesn't really, strike anything in us that would be of significance. But what if you look at it like this? One of our answers is negative 7/8 plus I squared of 23 over 8. And the other answer is negative 7/8 minus I squared of 23 over 8. Our answers, when we use the quadratic formula, are in fact complex conjugates. And they always will be. Always. You'll learn a little bit more in section 2.5, but the bottom line is complex answers to polynomials always occur in conjugate pairs. Complex answers always occur in conjugate pairs. And like I said, we'll learn more about that in section 2.5. All right, that's the end. Adios.